All right. Good morning. Sorry that we're getting a little later of a start than normal. There was a car accident on 231, and so traffic was basically stalled. Yeah, you guys can record. You two can record if you'd like. What I want to do here is, since there's not many people, I'm assuming because of this late start, I'm going to throw up a quick announcement onto your class so that people know that this is actually happening. So I'm typing a quick announcement and then I'll get into the class. There. We'll see. All right. Okay. So a few more of you are in. That's good. Yeah. As I was saying, there was a car crash on 231. So I was a little bit on the late side getting in as a result of that. Yeah, it didn't look like an especially bad crash, but they managed to shut down 231 northbound. So I basically ended up doing one of those U's and then finding a back road to get here, but it still took us a little extra time. All right, so what we're doing today, let me share the screen with you all so that you have that. All right. What we're doing today is that we're going to look at Amperes Law, which describes how charges can produce an electric field, how moving charges specifically can produce a magnetic field, and so basically the idea, first of all, is you can map out magnetic field lines by using a compass. I think I showed you this briefly in Friday's lecture, and so you have some compasses that are placed around this wire. There's no current. We turn on the current and immediately the compasses deflect, because remember that what's inside of a compass is basically a small bar magnet. The small bar magnet deflects such that the north end points towards the south end of the magnetic field, and so on, and vice versa. All right, and so in this thing's case, all of these compasses have deflected so that they are pointing along the magnetic field lines. Whereas with zero current, they all just kind of point to the magnetic, what we'd call the North Pole, the North Pole as defined by magnetic South Pole, but geographic North Pole, or near geographic North Pole. All right, so you can try to measure the magnetic field strength by using stuff that we saw from last time. For example, you could take a setup like this where you have a long straight wire, you've run some current through it, and you've got a little force sensor hooked onto it. and you put it partially into the magnetic field. If it's partially into the magnetic field, then you get a force on this side but no force on this side. So you have some net amount of force. These two sides cancel out as before. So you have a net amount of force. You can measure what that force is, and then you can work backwards to get that the magnetic field strength is like this. It's mu naught times I over 2 pi r, where I happens to be the current flowing in your long straight wire, not in the little wire on the diagram. Now we'll come back to this equation in a little bit. There's a new term in this equation, mu naught, which is 4 pi times 10 to the negative 7 Tesla meters per amp. It's called the permeability of free space. This is yet another fundamental constant of the universe. So, you should have that one written down in your notes. I think it is also in those handouts that I've put up that you can bring to tests and whatnot. All right. So a few things that we can do with this before we go into Amperes Law itself. In fact, maybe I'll do a couple of these and then I have a few polls to ask you guys, so that may be it. You have two long straight wires. They're shown in these two diagrams from the side and then from the top. They're separated by some distance r. You apply a current through both of them. It doesn't have to be the same current. In fact, in this diagram, they are not the same current. One of them is I1, the other one's I2. What's going to happen is you're going to have a force between those two wires, and the reason being that one wire produces a magnetic field, which then can act on the current, the moving charges in the other wire, and vice versa. All right, so using the equation on the previous slide, which is again written here for you, you can determine what the magnetic field strength is, B1, between the two wires. And since you have the magnetic field strength between those two wires, well, really produced by this wire, but acting on this one, you have B1. At this point right here, B1 would be in this direction. The current is coming out of the page at us. If we use the right-hand rule, you end up with a force that is to, would be my left, should be to your left when you're looking, as shown here. So that basically tells you how much force there will be is a B1 times the length of the wire L times the current I2 that's in the wire. And so sometimes we express it using a force per unit length, shown here, force over length. And so that should be the current in this wire times the magnetic field produced by this one. And then substituting our magnetic field in, B1, we end up with mu naught over 2 pi times I1. So that would be B1 over R. All of that is B1. And then that times I2. All right, so that is your force between two parallel wires. Now, a few questions that you might consider, and I think I should have a short quiz here. Maybe I'll give you one of the questions. It's not the one that's actually on the quiz. I'll type it out here because people told me in the later class that if you're on your phone and I start a poll, that the moment the poll starts, the question disappears. That's what they all told me. All right, so let's say that you have two wires. Let's say that you put current in opposite direction. So you have two wires. The current runs in, let's leave it like this. Let's say we runs in the same direction, e.g. as in the diagram. Okay, so you might want to draw the diagram that has two wires that are side by side like this, current going this way, just so you have that if this disappears when I start the poll. All right. Current is running in the same direction as in the diagram. Wires are parallel, so two parallel wires. And what we want to know is what direction will the force act in. Okay, we're looking at it from the side as in this diagram here. So here are some possible options. Both to the left, oops, both to the right, option C could be towards each other. Option D, away from each other. And what would, is there an A, B, C, D, E? Let me see here. We can have an A, B, C, D, E. All right, so let's give E none of the above. Nah, we'll do A, B, C, D. It should be obvious that it's not none of the above if I had to think about this. All right, go ahead. All right, looks like everybody's set a response. They also told me in the later class that you can't change your answer once you've put that in. I'm assuming that's in fact true. So since everybody's already put one, it looks like answer A, C, and D are the ones that people chose. So let me get out my dice. In case I need to do some rolling. Sydney, you have something? By the way, if it's easier to just say your answer than to type it, do feel free to pop on the microphone and answer that way. Okay, diagram F2 points to the left, so it cannot be B. All right, true. Yeah, if you look at the actual diagram in this figure, or in this one, the force that is showing is actually pointing to the left on this wire, and it is a correct diagram. So we should be able to eliminate option B, as you all have done. That's good. But that doesn't answer whether it's A or C or D. So, because it takes a little longer to respond via texting, I'm going to roll a few people and let you each put your answers in. So there was roll 1, roll roll 2, and roll 3. Okay, so I rolled Bethany, I rolled Georgia, and I rolled Paris. Oops. Guess. And more or less guess. Okay, so you've all guessed. That's fine. The next best thing is, were you able to actually eliminate any of the other 3 options, A, C, or D? You can type no if you were not able to, the 3 of you. I'm going to roll a few more people while you're at it, just to get us some variety. Not that this is a huge class or anything, but still. Okay, that would be Janavi and Junmin. What's going on here? All right. All right. Currents in same direction pull wires together, says Junmin. Okay. You have more explanation? So Junmin says he read ahead and saw on one of the slides that this is the answer. All right. Fair. That's fair. You found it on another one of the slides. All right, so we know that the correct answer, therefore, is actually C, towards each other, if it was already on one of the slides. Now, does anybody know why it would be towards each other? That basically means if we pull open our slides again, maybe. Takes its sweet time. There we are. That basically means that the force on this wire here, the wire that is to the left on the screen, that force must be somehow to the right. So how do we know whether it's to the right or to the left on that one? Okay. By the way, the fact that there is a force to the left on that wire that is to the right means you should have been able to also eliminate option D away from each other, because the force is clearly pointing towards the other wire. Okay, so really the question we're asking is there a force to the left or to the right of the wire that's on the left? And what you want to do is you want to basically redraw this diagram and this diagram, but now producing the magnetic field from this wire. Okay, so if you reproduce the magnetic field from this wire, then which direction will it be when it gets to this wire? Well, actually, it should be downward. So you should have a magnetic field down and you have a current coming up out of the page. So current coming up out of the page, field going down, means you have a force to this direction. This is my left hand. So this should be pointing to the right for you guys. My right hand, it actually points towards my right. So you have a force to the right. That means that you have a force to the right on the left wire, a force to the left on the right wire, and therefore the forces towards each other. So now we have an explanation for why it is towards each other. All right, before I do anything else, I wanted to work some sort of an example. Now, again, these are the examples that you have already on the video that I put up if you've been watching those. So I want to do some other example, like make up a different example than these. So let's see, where's my work pad? There's my work pad. So let's say you have two long straight wires, as always. All right, and these two long straight wires, they're parallel to each other. So two long parallel straight wires. They can be separated. Joseph, give me a number. Preferably like 1 or 2 digits. And Paris, give me a number. Okay, so separated by distance, we'll give it 6.0 centimeters with current 12 amps. Thank you. Current, we could either make it go in the same direction or opposite direction. The example that I want to work here, it doesn't really matter. We're just going to figure out magnitudes. So determine A, magnitude of B field. That could be produced by wire 1 at position of wire 2. And then B, magnitude of force from wire 1 to wire 2. We're assuming, by the way, 12 amps each wire. So they both have the same current. Okay, so how are we going to do that? So, whoops. Let's move this stuff up a little so that I have just a little bit of space to work on. And we'll switch to black. There we are. Okay, so for A, we can use the equation that we just had from the notes, the one that says that B is equal to 4 pi times 10 to the negative 7 times the current, let's see, where did my notes go, divided by 2 pi r. So in other words, we just make use of this equation right here, mu naught I1 over 2 pi r. So mu naught I1 over 2 pi r. All right. So mu naught is your 4 pi times 10 to the negative 7 Tesla meter per amp. I1 is 12 amps. That was our given up here. And then divided by 2 pi times the separation distance, 6 centimeters. So 6.0 times 10 to the minus 2 meters. All right, and we can cancel the pi's. 2 times 6 is 12, so we can cancel our 6's and 2's. We're left with 4 times 10 to the minus 5 Teslas. Okay, so that's the magnetic field strength at the position of wire 2 that's produced by wire 1. All right, so now we got to do part B. Part B is figure out the magnitude of the force. So this is per unit length, since I haven't specified any lengths. All right, and that would be your B from wire 1 times current I from wire 2. So that's 4 times 10 to the minus 5 Tesla. And then I2 was 12 amps. And so 12 times 4 is 48. So we end up with 4.8 times 10 to the minus 4 newtons. So not very much force, actually. Now, this actually lets us define, or maybe I should say redefine, a couple quantities from earlier. Quantities that we haven't really thought much about the definition in quite some time. You may have noticed that whenever we talk about charge on an electron or something like that, we'll say, oh, charge of an electron is 1.6 times 10 to the minus 19 coulombs. Now you may wonder, how did we get to this point? How did we get here? Why is the charge of an electron or of a proton such a weird number? You know, it's not even a round number. It's 1.60. Next digit's a 1, then there's another digit, and so on, digits, times 10 to the minus 19 coulombs, all right, charge of electron. In fact, I guess you could put a minus if you want it to be an electron. For a proton, it'd be plus. All right. So how was a coulomb defined? And an amp, you'll recall, 1 amp, we defined previously as 1 coulomb per second. All right, so that just follows from whatever the definition of a coulomb is. It turns out that we actually kind of have these two definitions backwards from each other. Though really we should be defining an amp first and then using that to define a coulomb. Now you may be wondering, how are we going to define these two quantities with an amp first? And the answer is, we can go back up to here and say, suppose that we have a magnetic field, okay, produced by 1 wire. And suppose that force per unit length on wire 2 is B1I2, as shown by the above. But suppose that we choose a force of 10 to the minus 7 newtons per meter. Okay, that's a really small number, but it's a nice round number. How much current would we need in the 2 wires, assuming that they have the same amount of current, in order to produce this force? Well, the first question is, well, okay, fine, how far apart are the 2 wires going to be? Well, let's give them a distance. Let's let the 2 wires be 1 meter apart, another nice round number. Okay, let R equal So B1 I2, remember that B1 is again 4 pi times 10 to the minus 7 times I1 divided by 2 pi times R. All right. So, and we've decided that I1 and I2 need to be equal to each other. Okay, so we'll just represent both of those by a current I. All right, that means that the force per unit length on wire 2, and likewise on wire 1, since it's the same current, if we eliminate our pi's, if we eliminate our 2 and turn this into a 2 right here, okay, and if we plug in all of our distances, then what we end up with is I squared times 2 times 10 to the negative 7 is somehow equal to, it's somehow equal to 10 to the minus 7 Newton per meter. All right, so now we eliminate the 10 to the minus 7s from both sides. We divide both sides by 2, and you end up with I is 1 over square root 2 amps. All right, now what if we decided instead that we're going to make the distance 2 meters? We'll move them 2 meters apart. What does that change? Well, then we can eliminate this 2 and this 2. We can eliminate this 2, and we end up with only 1 amp. All right, so this gives us a definition for the amp in terms of magnetic fields. Now we can define an amp to be the amount of current that needs to run through 2 long, straight, parallel wires placed so far apart such that you have 10 to the minus 7 newtons per meter of force per unit length on the pair of them. Okay, so we've now redefined the amp, and now that we have a definition for the amp, if the amp is 1 coulomb per second, then it follows that 1 coulomb is the same thing as 1 amp flowing for 1 second. Okay, so that's how much charge you need to have flow through an area through a cross section of a wire in order to get 1 coulomb in 1 second. And a coulomb, therefore, is how much charge actually flows in that 1 second if you have 1 amp of current. Okay, so now let's bring back our slides, because now I want to ask you what happens if we change the amount of current that the 2 wires have. Okay, so instead of having the same current for both wires, what if we decided to do different amounts of current for both wires? All right, so I'm going to copy and paste this over to the text so that you have it when I start the poll. Okay, so here's your question setup. Now let's see our 4 options. Okay, I'll give you 5 options. I'll give you all 5 of these. This way we can have an honest dunno. And we can have our 4 actual, these would be the kind of answers you'd get on the MCAT sort of options. All right, so let's start a poll, A, B, C, D, or E, and go ahead. We'll take maybe 2 minutes or until everybody's answered, whichever's first. while you guys are doing that, maybe I'll roll up who's going to be defending their answers so you don't have to wait on it. All right, so that was Bethany again, Bryson, and Aaron. Maybe one more. And Rebecca, you guys need to defend what your answers are, guys and gals. All right. About 30 seconds. Okay, everybody's got an answer in. All right, so overwhelmingly people have chosen option B. All right, so let's see what you guys have put. I guessed again, but B seemed like a good choice, says Bethany. All right, I'm moving this over again. Oh, it does this. You get the meta screen. I think I'm gonna not put that there because I'm afraid it may actually be part of why this thing crashes every so often. Okay, so Rebecca, you say, I put B because in the last example when we increased it to 2, it was 1 instead of 1 over square root 2, but I really don't know. We increased the distance in that one, not the current. That's something worth noting, is we did not increase the current. B as a guess. And Bryson, do you have something? Oh, he's gone. Okay. All right. Well, the actual answer, it turns out, was not B. It's actually C. Now, there's 2 ways that we can go about getting this answer. One way that we could do it is we could go and actually try to calculate how much B field is this one producing, and therefore what's the force? How much B field is this one producing, and therefore what's the force? And that will get you the correct answer. It's John Avi now types, I feel like the answer is C, but I'm not sure. Yes, it is C. That is correct. How you can get that, one way is you can go and actually calculate the magnetic field and then calculate the force per unit length for both wires. The other way, the way that we like to come back to, and you've seen this a few times in Physics 1 and a few times in Physics 2, it will show up, there's a good chance, on the MCAT somewhere because it's such a great kind of question. And you can see why. It's because not many people got the answer right. So this would come in as like one of those challenger questions. But it turns out all you need to apply is your Physics 1 knowledge and use Newton's third law, which says that the force that object 1 applies to object 2 and the force that object 2 applies to object 1 must have equal magnitudes in opposite directions. So by Newton's third law, we can actually skip all of the other calculations and see that it is in fact the same force. This is an actual Newton's third law pair that you were just asked about. So always be sure to check and see, is there a Newton's third law pair in the question? So we've come basically to the end of what I wanted to accomplish with today's class. We will do Amperes Law in this next course. What I wanted to ask one last poll, and this is more of a it's more along the lines of logistics. And I wanted to type the poll question for you. It's basically just, do we want to keep doing the virtual classes via Canvas conference or try Teams? Okay, and basically you can do like true. Now let's say A would be Canvas, B can be Teams, and C could be either is fine. D, can I do ABC? Can I just do ABC? Yeah, I can just do ABC. I don't have to make up more options. D, 8 o'clock is too early to come to class. No, we do ABC. All right. And I asked this because some people in the comments in the other section were suggesting Teams. So if either is fine, looks like most people are putting C. All right, so maybe we will continue with these. Now I've been recording this entire thing as best I can. We'll see if the recording works. We'll see if the microphone worked. But I will try to post it onto YouTube, and therefore anybody who's not here will have something to watch. Although it may not be the most exciting watching, especially when we're doing a quiz and it's like silence for 2 minutes and then typing for 2 minutes. All right, well, thanks everybody for responding, and I guess we will adjourn for today. Be sure to check for your lab and to be working on your labs. Those of you who are in my lab sections, which is most, though not, I think just most, though not quite all of you, especially for the people who didn't attend today, maybe a few aren't in my lab either. You may work on the labs. You can create your own collaborations either in Canvas or via Teams if you would like to have 4 people work on the lab or 2 people or whatever. Just as long as everybody's name is on the lab that is submitted, then that will be fine. Otherwise, you can submit it 1 per person, and I think I've enabled it so that you can submit it electronically via Canvas at this point. So if you're not on or near campus and or don't want to come to campus, which probably is true anyway because I think the doors are all locked on the building, then just submit it. The other thing is that we will obviously not have a test this week. We originally were going to have our test. It would have been this coming Friday, but I'm going to postpone it for now until at least next week. But we will need to discuss in one of the near classes how we want to do the exam, and I have some ideas on that. In fact, I have one idea for it that is probably how we will try it, but I don't want to keep you any later. So thanks everybody for attending, and I will see you on Wednesday, unless you come to the office hours. By the way, the poll results, if you can't see them, almost everybody just said C, so either's fine. The only person who didn't say C said A, which is Canvas, so I think we'll just keep doing them this way for now. But I may try the teams with the other section just because that's what they're asking for. All right, so I think that's good. See you all on Wednesday, at least virtually. So long.